The secondary side of a control voltage transformer should not be bonded to the equipment grounding conductor. The primary side of the transformer is connected to the line voltage, which is typically 120 or 240 volts. The secondary side of the transformer is connected to the control circuit, which is typically 24 volts. The control circuit is used to power components of the heating, ventilation, and air conditioning system such as the thermostat and fan motor. Bonding the secondary side of the transformer to the equipment grounding conductor can create a ground loop. A ground loop provides a path that allows current to flow from the line voltage side of the transformer to the control circuit side. This current flow can cause the control voltage transformer to overheat and eventually fail. The initial transformers failed because they were bonded to the equipment grounding conductor, creating a ground loop situation, and the third transformer did not fail because the ground was not connected, eliminating the unwanted current path. Grounding the secondary side of a control voltage transformer to the equipment grounding conductor is not a common practice, and it is generally not recommended. If there's uncertainty about grounding the secondary side of the control voltage transformer, an electrician should be consulted. A control transformer steps down voltage from a higher level, like 120 or 240 volts, to a lower level, typically 24 volts, for use in control circuits. These circuits power relays, solenoids, and other control devices in HVAC and industrial systems. Grounding refers to connecting a circuit or equipment to the earth, providing a path for fault current flow, which helps protect against electrical shock and equipment damage. The equipment grounding conductor is a safety wire that connects the non-current carrying metal parts of electrical equipment to the grounding system at the service entrance. A ground loop occurs when there are multiple ground paths in a circuit, creating a loop that allows a wanted current to flow. This current can cause noise, interference, and equipment damage. A control transformer consists of a primary winding and a secondary winding. The primary winding is connected to the higher voltage source, and the secondary winding provides the lower voltage for the control circuit. The purpose of a control transformer is to isolate the control circuit from the line voltage and provide a stable voltage supply. The primary side of the transformer should be properly grounded to ensure safety and prevent electrical shock hazards. The secondary side, however, should generally not be grounded unless specifically required by the equipment manufacturer or local electrical codes. When the secondary side is grounded, it can create a ground loop if the control circuit also has another ground connection. This ground loop can cause circulating currents that overheat the transformer and lead to premature failure. Firstly, ensure that the primary side of the control voltage transformer is properly grounded according to the National Electrical Code, Section 250. Secondly, verify that the secondary side of the transformer is isolated from ground, unless specifically required by the equipment manufacturer. Thirdly, check the control circuit for any unintended ground connections that could create a ground loop. Fourthly, use a multimeter to measure the voltage between the secondary side of the transformer and ground to ensure that it is within the specified limits. Fifthly, consult with a qualified electrician to review the wiring and grounding of the control transformer and associated circuits. Understanding grounding principles is crucial for maintaining the safety and reliability of electrical systems. Improper grounding can lead to equipment damage, electrical shock hazards, and even fires. By following the recommended practices and consulting with qualified professionals can prevent these issues and ensure the safe operation of electrical equipment. In most cases, the secondary side of the control voltage transformer should remain isolated from ground to avoid ground loops. However, there are specific situations where grounding the secondary side may be necessary. For example, some equipment manufacturers may require it for safety reasons, while local electrical codes may mandate it. In these cases, it is important to follow the manufacturer's instructions and code requirements carefully to ensure that the grounding is done correctly. Firstly, determine if the equipment manufacturer requires the secondary side to be grounded. Secondly, check local electrical codes for any specific grounding requirements. Thirdly, use a single point grounding method to avoid ground loops. Fourthly, ensure that the grounding conductor is properly sized and connected. Fifthly, verify the grounding with a multimeter to ensure that it is effective. In addition to grounding, there are other important considerations for control voltage transformers. Firstly, select the correct transformer size for the application to avoid overloading the transformer. Secondly, protect the transformer with properly sized fuses or circuit breakers. Thirdly, ensure that the transformer is properly ventilated to prevent overheating. Fourthly, regularly inspect the transformer for signs of damage or wear. Fifthly, replace the transformer if it shows any signs of failure. The National Electrical Code (NEC) provides specific guidelines for grounding and wiring electrical equipment. It is essential to follow these guidelines to ensure safety and compliance. The NEC Section 250 covers grounding requirements for electrical systems. NEC Section 430 covers motor circuits and motor control circuits. NEC Section 600 covers electric signs and outline lighting. NEC Section 725 covers Class 1, Class 2, and Class 3 remote control, signaling, and power limited circuits. It is important to consult the latest edition of the NEC and any applicable local codes when installing or modifying electrical systems. A ground fault occurs when there is an unintentional electrical connection between a live conductor and ground. This can happen due to damaged insulation, loose connections, or other faults. Ground fault circuit interrupters (GFCIs) are designed to detect ground faults and quickly disconnect the power to prevent electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas to protect people from electrical shock hazard. Arc faults are another type of electrical fault that can cause fires. Arc fault circuit interrupters of size are designed to detect arc faults and disconnect the power to prevent fires. SIs are required in many locations, such as bedrooms, to protect people from arc fault hazards. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect electrical circuits from overloads and short circuits. These devices are designed to trip and disconnect the power when the current exceeds a certain level, preventing damage to equipment and wiring. It is important to use the correct size overcurrent protection device for each circuit to ensure proper protection. Surge protective devices (SPD) are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power grid switching. These devices divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are recommended for protecting computers, televisions, and other valuable electronic devices. Electrical safety is paramount when working with electrical systems. Firstly, always disconnect the power before working on any electrical equipment. Secondly, use insulated tools to prevent electrical shock. Thirdly, wear appropriate personal protective equipment (PPE), such as safety glasses and gloves. Fourthly, never work on electrical equipment in wet or damp conditions. Fifthly, if unsure about something, consult with a qualified electrician. Electrical troubleshooting involves identifying and resolving electrical problems in a systematic manner. Firstly, start by gathering information about the problem. Secondly, inspect the equipment and wiring for any obvious signs of damage. Thirdly, use a multimeter to measure voltages, currents, and resistances. Fourthly, use a process of elimination to narrow down the possible causes of the problem. Fifthly, once you have identified the cause, repair or replace the faulty component. Regular maintenance is essential for keeping electrical systems in good working order. Firstly, inspect electrical equipment and wiring for any signs of damage. Secondly, tighten loose connections. Thirdly, clean electrical equipment to remove dust and debris. Fourthly, test GFCIs and FSIs to ensure that they are working properly. Fifthly, keep electrical panels and equipment rooms clear of obstructions. Ground resistance testing is a method used to measure the resistance of the grounding system. This test helps ensure that the grounding system is effective in providing a path for fault current to flow. A low ground resistance is essential for safety and proper operation of electrical equipment. Insulation resistance testing is a method used to measure the resistance of the insulation on electrical conductors. This test helps identify damaged or deteriorated insulation, which can lead to electrical faults. A high insulation resistance is essential for preventing electrical shock hazards and equipment damage. Thermography is a non-invasive method used to detect hot spots in electrical equipment. This technique uses an infrared camera to measure the temperature of electrical components. Hot spots can indicate loose connections, overloaded circuits, or other problems. Thermography is a valuable tool for preventive maintenance and troubleshooting. Power quality analysis is a method used to measure the quality of electrical power. This analysis can identify voltage sags, swells, harmonics, and other power quality problems. Poor power quality can cause equipment malfunctions, data loss, and other issues. Power quality analysis is essential for ensuring the reliable operation of electrical systems. Harmonics are distortions in the electrical waveform that can cause various problems, such as overheating, equipment malfunctions, and increased energy consumption. Harmonic filters are used to reduce the levels of harmonics in electrical systems. These filters are designed to absorb or block harmonic currents, improving power quality and equipment performance. Energy efficiency is an important consideration for all electrical systems. Firstly, use energy-efficient lighting, such as LED lamps. Secondly, install programmable thermostats to control heating and cooling systems. Thirdly, use variable frequency drives VFD to control motor speeds. Fourthly, turn off equipment when it is not in use. Fifthly, conduct regular energy audits to identify opportunities for energy savings. Variable frequency drives VFD are used to control the speed of electric motors. These devices can save energy by reducing the motor speed when it is not needed. VFD also provides soft starting, which reduces stress on the motor and connected equipment. Uninterruptible power supplies UPS are used to provide backup power in the event of a power outage. These devices can keep critical equipment running during a power outage, preventing data loss and downtime. UPS are essential for computers, servers, and other sensitive electronic equipment. Power factor correction is a technique used to improve the efficiency of electrical systems. Power factor is a measure of how effectively electrical power is being used. A low power factor can result in increased energy consumption and higher utility bills. Power factor correction capacitors are used to improve the power factor and reduce energy losses. Electrical safety audits are used to identify potential electrical hazards in the workplace. These audits involve a thorough inspection of electrical equipment, wiring, and grounding systems. The results of the audit are used to develop a plan for correcting any identified hazards. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the power and placing a lock and tag on the disconnect switch to prevent it from being turned on accidentally. Lockout/tagout procedures are essential for protecting workers from electrical shock hazards. Confined space entry requires special precautions to protect workers from hazards such as toxic gases, lack of oxygen, and electrical hazards. Confined spaces should be properly ventilated and tested for hazardous conditions before entry. Workers should be trained in confined space entry procedures and wear appropriate personal protective equipment. Electrical codes and standards are constantly evolving to keep pace with new technologies and safety concerns. It is important to stay up to date on the latest codes and standards to ensure that electrical systems are installed and maintained safely and efficiently. Continuous learning is essential for electrical professionals. There are many opportunities for continuing education, such as attending seminars, taking online courses, and reading industry publications. Staying current with the latest technologies and best practices is essential for providing high-quality electrical services. By understanding grounding principles, following recommended practices, and consulting with qualified professionals, electrical problems can be prevented and ensure the safe operation of electrical equipment.